Next talk will be by Bijay Agarwalla from IISc Pune on anomalous transport and long-range lattice systems.
Okay, yeah. Thanks, Srijit. So let me begin first by thanking the organizers for the kind invitation and giving the opportunity to talk about some of our recent works. Okay, so what I'm going to talk about is anomalous transport in long-range lattice systems. So we have been looking at this problem for a few years now, and so I'm primarily going to talk about these three papers. Just to give a sort of a complete picture, reasonably complete picture, I have to talk about somewhat old paper, which is this one, and yeah. So basically, the entire talk is going to focus on these three. And most part of the talk, the kind of setup I have is in my mind is very simple, where you have some kind of a lattice chain which is having some kind of a long range interaction, which we call a power law kind of long range hopping, which has this exponent alpha. So that is the system, and what you do is you connect these two systems with two baths at the two ends, which we call as boundary driven system, and put them at different chemical potentials, and then wait, the system goes to the steady state, and you basically look at the current. And you try to understand what properties you get for the current. So that's the kind of setup that I'm going to focus on for most of the talk. So here is the outline. So since I'm going to talk about anomalous transport, I'm just going to give you a very brief background of what exactly anomalous transport mean. And then, as I said, I'll first focus on steady state properties, the transport properties. First, for a clean long range system, and I'll mention what I mean by clean. And then we'll make the problem a little bit more non-trivial by adding some kind of noise source, which we often call as dephasing sources on top of these long range systems, which kind of mimics this kind of setup. And another way to study, the last part of the talk would be, another way to study transport is not by looking at steady state, but you can also do time dynamics. You create some single, you look at evolution of a single particle wave packet and characterize transport from that sense. So that's going to be the last part of the talk, and then I'll basically summarize. Okay, in terms of quantum background of quantum transport, most of you are aware. In the steady state, the way we quantify transport is by looking at the scaling of conductance. So if you're at the linear response, you basically look at conductance and look at how it depends with the varies with the system size. If you have a normal conductor, the conductance basically goes as inverse of the length of the system, or resistance goes proportional to the system size, and as a result, resistivity or conductivity becomes independent of the dimension of the material. So that's what we typically call as normal conductor, or when we say normal transport, what we essentially mean is that the conductance, if we look at, it goes as 1 by n, where n is the size of the system, the number of lattice sites that you have in one dimension. Okay, but that's not the only, if you look at low dimensional system, that's not what always happens. In fact, depending on the how conductance behaves with system size, you can classify various transport regions. For example, if conductance is independent of system size, it's what we classify as ballistic transport. There could be situation where conductance is exponentially localized with the system size, where this zeta is like the localization length, and this is, yeah, so this is like a perfectly insulating kind of a situation. Apart from these two, what also you can have is conductance goes as some power law with the system size. Where look at this delta, so depending on the value of delta, you further classify the different transport region. For example, if delta equal to 1, then of course it's a normal or what we call diffusive transport. But if delta is between 0 to 1, you call that is faster than diffusive in a sense. It's called what we call super diffusive transport. And if delta greater than 1, you call it subdiffusive transport. So this is, in fact, this is the region which we often call as anomalous transport region, like which deviates from the diffusive. So if you have anything delta which is not equal to 1, you tend to call it anomalous. So what I'm going to show is that this long range system hosts this kind of various kind of anomalous transport. About subdiffusive transport, you can ask like what kind of systems you often see this transport happening. You often find for example, systems which lie at the critical region, separating localization and delocalization region, or even systems which has, correlated or uncorrelated kind of disorders. So for example, in quasi-periodic systems, you tend to see subdiffusive behavior. But what I'm going to show you is that even if you take a very simple, clean, long-range lattice system which doesn't have any disorder, there is some kind of a subdiffusive transport that you can get. So with that, let me start the first setup. So before in fact I go to that, let me just say that the long-range lattice models are now very much realized in various experimental setups, in well-controlled setups, and in fact Sanjukta also in her talk mentioned that one can actually control this kind of interactions and can generate long-range interactions. So there are now many experimental papers that are coming up, and people are looking at various interesting physics, namely, for example, pre-thermalization, dynamical phase transitions, measurement-induced phase transitions, and so on. There are many interesting physics that these kind of setups are giving rise to. Okay, so with that, let me come to what the question that we are asking. So what we have is a simple one-dimensional long-range fermion chain without disorder. So it's a clean system which basically given by this Hamiltonian, and the point to note is that there is this power law long-range hopping with exponent alpha. So that's the system, and what you do is basically you connect this system with two boundary reservoirs or baths, which are always which are quadratic, and the standard system bath coupling, which basically allows particle exchange between system and bath. And you keep these two baths. So at this point, what I'm going to talk about is baths are at 0 temperature, but there is some tiny chemical potential difference. So I'm kind of in a linear response region, and what I'm interested in looking at the non-equilibrium steady state properties. So and I'm basically asking what is the system size dependence of conductance in this very simple non-interacting setup rather. That's a very simple question. We know almost everything in a sense that we know how to calculate conductance. Yeah.
Previous slide.
Yeah.
So these are bosonic oscillator modes?
No, these are not bosonic, these are fermionics.
Okay.
Yeah, these are fermionic operators which exchange, these are baths, and this coupling is allowing particle hopping between the system and the bath. This L. Oh, so this is written in the diagonalized representation. So this you can think of all the K vectors. Okay, so in the linear response, you can basically write the Landauer formula. In the linear response, the conductance is given by simply the transmission function, which basically tells you with what probability electron goes from one end to the other, and the derivative of the Fermi function. But if you take that's the Fermi-Dirac distribution. And this transmission function you can write in terms of the so-called the Green's function, which depends on one n. That means the first site and end site, this particular component, what gives rise to, contributes to the transmission. Of course, at 0 temperature, the derivative of Fermi function is a delta function. As a result, the integration goes away, and you get a very simple formula for conductance evaluated at the chemical potential, which you can tune. So that's simply given by the transmission over 2 pi. So in order to now find the system size dependence, all you have to know what is the system size dependence of these Green's functions. And this Green's function has a, what is the expression? It's essentially the single particle Hamiltonian, and which is also dressed by the self energies coming because of the boundary reservoirs. So that's a single particle matrix, and this is a self energy matrix. And you can right away ask, what do you know for short range systems? So that has been well studied. So if you look at short range system, and if you so mu is something that you can vary. So if you keep your mu within the band of the lattice, then of course you will see that the conductance doesn't scale with system size. It can oscillate at max. So as a result, it's a ballistic transport. On the other hand, if you take mu outside the system band, the transport gets exponentially localized with system size, and so this is what happens for short range system. But our task is to look at what happens for long range. So before getting into the open part, at least you can try to ask what happens for just looking at the isolated system. And you can solve for the dispersion relation in the thermodynamic limit. which is given by this expression. So these are the eigenvalues, the single particle spectrum, which has some interesting properties. So first property is that this is an infinite series, because the series is coming because it's a infinite, it's a long range interaction. The first observation is that this series converges, absolutely converges for alpha greater than 1 for all k. So what I'm going to do is all the time going to take alpha to be greater than 1. So that's the first thing. And of course, if you look at the single particle eigenvectors, they are completely delocalized. So these two information you have, but there is something more to it. What you can actually show, or you can even see here, that this quantity is non-analytic at k equal to 0. So this is somewhat going to play a very important role in the sense that you pick one alpha, and if you take p, you can actually show the derivative, the pth order derivative, which is given by p greater than alpha minus 1, that diverges. So in that sense, at k equal to 0. So in that sense, this function has this non-analytic behavior, which is going to be very important. And the other two things that I want you to note is that, of course, you can look at the band edges, and these are located at 0 and plus minus pi, as usually happens. And these band edges values, the energies are given by some zeta functions and so on. So this is just because we are going to now look at what happens to the transport. Okay, so let me first put the results. So this is now the conductance as a function of mu. Yeah.
Does the system have, the single particle spectrum have gaps, or?
Single particle spectrum.
It's a single band.
Yeah, it's just a single
sorry,
band.
sorry.
It's just a single band, exactly. You just, right. Okay, so this is conductance as a function of mu. So these two vertical lines are basically the band edges of the system. So if you look at, and this is plotted for different ends. So if you look at here, you can right away say that, okay, this is not, there is no n dependence. So it's kind of within the band, it looks like it's ballistic. But if you look at outside, there is n dependence that are showing up. And if you do a scaling by n raised to 2 alpha, where alpha is that long range exponent, you see nicely this outside region, the outside of the band edge region perfectly collapses. So that's one observation. And if you do further a log-log plot of the conductance versus n by taking different mu's. So for example, if if you're going outside the band, so which is for example these and this, so this is outside of the lower band and this is outside of the upper band, they have a perfect 1 over n raised to 2 alpha scaling. Whereas if you are within the band, it's like a flat, which is n0, so that's like ballistic. And if you are at the band edge, which is precisely this cross points, so these are the two band edges, and that's where you see perfect 1 by n square fitting. So essentially the summary of this, if you draw a phase diagram, is essentially this, that you have mu and you have alpha. So what you get is, and these two are band edges, which are also functions of alpha. So if you are at the band edges and look at the conductance scaling, they are always 1 by n square. In fact, it's independent of the index alpha. So at the band edges, it's a subdiffusive. As well as if you are outside the band edge, which is this region and this region, that's also is subdiffusive, but it depends on the exponent alpha. So there is 1 by n2 alpha dependence, and within the band you don't see any signature of it. It's completely ballistic.
And if I had a perfectly short range model,
if you had short range model,
What-
n0, n minus 2, and this will be exponentially localized.
could you repeat that? Sorry.
So if you are doing this exercise for short range model, it will be n0 within band. Band edges, it will be still n raised to minus 2 or 1 by n square, because it's independent of alpha. So you can even take alpha infinity, which is like a short range. Outside the band edge, it becomes exponentially localized. So yeah, so that's precisely the point, that what the region which was exponentially localized now got a power law or subdiffusive kind of dependence because of the long range hopping. What is the? So that's basically the imaginary part of the Green's function. No, that I'm not, I cannot recall how the density of states. Okay, so subdiffusive phases at and outside band edges. So we got little intrigued at this point that why band edges, it's such a universal exponent, which is 1 by n square, which is independent of alpha. So turned out there is a remarkable connection you can explain sort of in a mathematical sense. Yeah. The van of uh, uh, right, right, okay. Yeah. But note that, I mean, so the couplings can be in fact arbitrary. So we have checked that. I mean, even if you have these boundary couplings to be arbitrarily strong, you still get system size dependence exactly to be of this form. That's one. The second is that if you just do this experiment on an isolated system, you will not be able to extract anything which is outside the band, right? I mean, what do you mean even outside the band? Because the chemical potential you can tune only by having these reservoirs, which can help you to tune this chemical potential. So that's another, what we observed is that this 1 by n square scaling, you can actually, since this is independent of alpha, that means it's even true for short range system. So what we found is that there is a nice connection of you can explain this 1 by n square behavior by constructing a transfer matrix for this, let's say a tight binding lattice, let's say a short range model, and turns out such a transfer matrix is non-Hermitian in general, and they host something called exceptional points when mu corresponds to band edges, and this exceptional point physics gives rise to, at least mathematically speaking, such 1 by n square scaling. So we looked at sort of this transfer matrix approach and connecting to conductance and exceptional points. So if you're interested, you can look at some of our papers in this direction. Okay, now if you look at, for example, chemical potential profile, what kind of signature do you have? If you are at the band, within the band, as I said, I mean, it's oscillatory, the chemical potential profile. But if you now, for example, locate it outside the band edges, which has these subdiffusive exponents, if the system was perfectly localized, you would have expected such a chemical potential profile. But because of the subdiffusive nature, you have essentially, as you keep on increasing alpha, you sort of tending towards sort of more and more localized sort of a direction. So that's the chemical potential profile. So you can ask what is the origin of this subdiffusive scaling. So at least again from a mathematical aspect, so the reason of appearance of this, at least you can explain from the fact that there is this non-analyticity in the dispersion relation. So that turns out to be very crucial. So in order to extract system size scaling, what you can do is essentially you have to do some kind of analysis of where the poles are located for this denominator. So this is essentially you're writing the Green's function in the K space. So you can easily figure out that if you take mu within the band, then you're gonna get the solutions for K to be real, which at best can give you oscillatory solutions. So that explains why you within the band expect ballistic kind of behavior. But when you're at the lower band, let's say you're at the lower band, the maximum contributions you're gonna get for small values of K, which is like K around K equal to 0. And if you now look at the dispersion relations around K equal to 0, you have this non-analytic term. Because as I said, the function is non-analytic around K equal to 0. So this non-analytic term is what, if you now properly take that into account and try to evaluate using some contour integration, you see that the Green's function now scales as n raised to minus alpha, and as a result, the conductance scales as minus 2 alpha. So precisely this non-analyticity of the dispersion relation, which brings it this kind of anomalous subdiffusive scaling outside the band edges. One can also ask what happens, it's a non-interacting setup, but if you now take many-body interactions, are these subdiffusive phases robust? So one can actually argue that they will remain robust, and that has a very simple reasoning. So as long as you have some number-conserving Hamiltonian, interacting Hamiltonian, these subdiffusive phases will be robust, and that can be followed from the argument that if in absence of many-body interaction, if you look at this quantity gamma, which is like what's the particle density outside the band edges, and that has sub-extensive number of particles. So if you make your system size larger and larger, you have very few particles essentially, which as a result, if you even put many-body interactions, I mean, they will not get any dominant contribution. So this kind of subdiffusive phases going to be robust against many-body interactions. So okay, so yeah, so this is so far just a clean long-range lattice system, boundary-driven, and we saw that at zero temperature, there are, if you vary this chemical potential at the band edge and outside band edges, you get these interesting subdiffusive phases. One can now ask, if I sort of now put this long-range model in presence of some kind of interactions, that's typically a harder problem. But there are ways you can actually take some kind of interactions into the system, and that's what precisely is the next part of the talk. So what we basically do is we take again this long-range lattice. We have a boundary drive, but on top of that, what we do is add some kind of a noise term which we call dephasing. I mean, it's probably quite standard. And we model the whole thing in terms of quantum master equation or Lindblad equation. So this is the Lindblad master equation, which has the unitary part. And if you look at this L and R, which are nothing but, so okay, so I think, yeah, so this is basically the setup. You have the lattice again, you have long range hopping, you have the two boundary reservoirs, but the new ingredient is that you have the so-called dephasing Lindbladians, which kind of mimicking interactions. Which are also number conserving, by the way. So whatever particle comes in goes out in that direction. So they are number conserving. So let me just explain the various terms. So the long range coupling goes into the Hamiltonian. And if you now look at these are what we call dissipators. So this dissipator is basically injecting particle to the system from the left end. This dissipator is extracting particle from the right end. And if you look at the dephasing, which are basically number conserving dissipators, are given by these interactions. These are on-site dephasings having the strength gamma. So the question that we are asking now, as a function of gamma, if I tune gamma, what kind of transport behavior you see? So that's essentially the question that we are asking here. And what are the observable of interest? You can right away calculate, for example, the steady state occupations or the density profile, and as well as current, and look at the scaling of current as a function of system size. So basically, all you have to compute is single particle correlation matrix, because that right away going to give you the densities as well as the currents. And turns out that this is the peculiarity of this model, that even if the Lindblad, which is quartic, because you have two ends, which are the number operators, so this is a quartic sort of dissipator, but even you have that, the 2-point correlation, the equation of motion, if you look at it, closes. So it doesn't generate the hierarchies, which you typically expect if you have many-body interaction. And the reason perfectly lies on the fact that these operators are Hermitian. So because these operators are Hermitian, you are getting this a nice closed set of equation, which you can then solve and get these quantities. And if you don't have dephasing, this actually, so if you put this gamma to be 0, this equation becomes a famous equation called Lyapunov equation. But otherwise, it's a slightly more involved equation, but it's still closed, doesn't generate hierarchy. However, the underlying system, the system is actually very non-Gaussian. I mean, even though 2-point closing in 2-point, you still do not have Weeks theorem. I mean, if you look at, for example, 4-point, it doesn't breaks into product of 2 points. So that's, so it's still non-Gaussian, but 2-point closes in 2-point. Okay, so then if you look at now the density profile, as a function of alpha. So let us just look at alpha greater than 1. Let's not pay attention to smaller values of alpha. So what you see is that if alpha is large, you get a perfect linear profile, which we actually indicates is a diffusive transport. But on the other hand, if alpha is smaller than some number, you tend to have a very different looking profile. So that's the density profile. But now let's look at the conductance or basically, so here I'm plotting resistance, which is inverse of conductance. So if you look at resistance, this is a log-log plot. So you see that it's all linear. So that means it's following some power law. And certainly now you can ask what is this nu, because then that will tell you what kind of transport is happening. So if you now plot this nu as a function of alpha, what you see is that starting from 1 to up to some value which numerically, given the limitation of system size, I think we went up to 1024, there is nu is less than 1 up to around 1.6, and after that it smoothly goes to 1. So roughly this figure is indicating that there is a crossover. If nu is becoming 1, that essentially indicates there is a diffusive transport. And in this region, it's essentially because nu is less than 1, so this is indicating a super diffusive transport now. So as a function of alpha, you see the moment, so once you have this dephasing, you now have another transport region as a function of alpha, which is basically from super diffusive to diffusive. So this is expected, at least for strong alpha, large alpha, we know what to expect, because large alpha means the system is becoming short range, and there it's well known that if you have a short range and you put this kind of dephasing, it should go to diffusive. So this is not very surprising, but what you get here is kind of interesting, that it's a super diffusive. And if you calculate this nu, if you fit this nu, it actually follows this relation with alpha. So nu is 2 alpha minus 2 between 1.6. And of course, this is within numerical accuracy. So we sort of believe that the actual transition or actual crossover happens at 1.5, alpha around 1.5. So basically how you argue that whether it's alpha 1.5 or not, I mean, it's not a very trivial, we didn't find a very solid sort of a reasoning, but what we started looking at is, in absence of dephasing, we asked if we calculate the operator norm for the current, so which basically gives you the bound or bound on the maximum allowed current. So if you look at that, it actually has a sort of different behavior as a function of L when this alpha is less than 1.5 versus greater than 1.5. In fact, for greater than 1.5, it's actually independent of L. And if it is independent of L, you sort of, the conjecture is that if you put dephasing, it should take you to diffusive. And whereas this is alpha less than 1.5 is actually diverging with L, and you expect that if you put dephasing on top of this, you probably should expect a super diffusive transport. But that's at a very conjectural level. So I just want to mention that, this kind of transitions, in fact, this alpha 1.5 transition has been seen in various contexts. I mean, one of the contexts is this measurement-induced phase transition in long-range systems. And there also it was perfectly that it was shown by Keiji Saito's group that if you have alpha less than 1.5, then there is no MIPT, no matter what gamma, which is the rate of measurement. There is no MIPT, but if you make alpha greater than 1.5, you have a volume to area law transition. So this alpha equal to 1.5 is sort of an interesting point. So if you look at the heat map for the current, okay, I'm not making any connection. I mean, in fact, it's very hard, I believe, but it also has some nice crossover in terms of 1.5. Okay, so these two sort of setup where we looked at the steady state transport for long range system in absence and in presence of interactions. So now you can ask, what about time dynamics if you do in long range systems? So what do I mean by time dynamics? So essentially, what I have is the long range lattice, but I don't have any boundary reservoirs. So in that sense, I will never get a steady state. So I take this long range lattice and I just put these interactions, the dephasing sort of. So I basically remove the boundary reservoirs and have the lattice and the dephasing, and I just have a single particle excitations and basically look at how it spreads. So I'm interested in single particle dynamics, which is essentially a single particle correlator of this kind. And if you look at it satisfies, as I said before, it closes, the equation of motion closes, where this is the unitary part and this is the part which is mimicking the dephasing. And here I have denoted it kappa, which is the dephasing strength. So if you now keep a single particle, let's say at the middle of the lattice, and evolve this, it's basically going to give you the single particle profile. And you can ask how this profile essentially evolving as a function of time. So that's basically the question. So you can either solve this equation, so that's one approach, straightforward. The other approach that you can take is basically you can unravel this Lindblad dynamics. So when you do unravel, basically, so you basically make it a kind of a stochastic process. So in this case, you can unravel it as by adding some noise, which is coupled to the local density. And this noise, if you make it delta correlated Gaussian noise, then of course, if you do average over this actually mimics this Lindblad equation. So what you can actually also do is like a stochastic trajectory kind of a thing. You basically evolve with this Hamiltonian and can calculate this single particle propagator average over noise realization, and that can also give you the profile. So these two are a completely equivalent approach. So what do you expect? If you look at this density profile for an initially localized particle in the middle and you let it evolve, you expect typically that the profile has this kind of a scaling form. And what you see here is that once again, for certain dephasing strength, if you have alpha less than 1.5 versus alpha greater than 1.5, you have two different scaling functions and fitting, completely different fitting. In one case, it fits with t raised to eta, in another case, it fits with t raised to half, which is again indicating a diffusive kind of a transport, whereas for alpha less than 1.5, the fit is with the exponent eta, which is 1 by 2 alpha minus 1. So the time dynamics also, which is again sort of indicating that it's a super diffusive transport, and yeah, it's not really okay. So this is still a reasonably small time. I mean, there are these tails. So if you make the time longer and longer, you will actually see a better prediction too. So there are finite time corrections that yeah. So how do you explain this profiles? Turns out you take this single particle equation, and if you at least take the limit of large dephasing, so you take a limit kappa, which is the dephasing strength, much larger than the hopping, turns out you can actually show that the equation, the single particle equation, it actually follows a fractional diffusion equation. So that's interesting, and in fact, if you make this alpha to be large, then it boils down to standard diffusion equation. So that immediately tells you that for alpha large in presence of dephasing, you expect a diffusive behavior for short range system, with the diffusion constant being this quantity. So if you solve this fractional diffusion equation, in the large system size limit and so on, you can actually show that there are two different scaling functions for alpha less than 1.5 and alpha greater than 1.5. And this is the scaling function for in the super diffusive region, which is a family of stable distributions. And if alpha greater than 1.5, it turns out to be a Gaussian distribution. So with that, I would like to summarize. So what I showed is that, I mean, these long range systems host interesting transport properties, and in the clean lattice system, we observe anomalous subdiffusive regions, and if you put interactions or mimic interactions through dephasing noise, there are some nice crossover from super diffusive to diffusive transport region if one tunes the long range exponent. So before I end, I should thank students and other collaborators. So Madhumita and Archak did they mostly primarily did the clean long range setup. So Madhumita was a postdoc in my group, and she's now a postdoc in ICTS. Katha is a PhD student in IISr Pune in my group. Avina was a master's student in IISr Pune, who is also in the audience, who has joined ICTS as a PhD student. And I have other collaborators who also lead these projects. Archak, Devendra, who is in ICTP, Manas, who is here, and Shubhajit. So with that, thank you for listening to this.
Vijay, in your first setup, you showed that the fermionic term doesn't affect the result.
Interaction term.
Interaction. So interaction, did you treat at the mean field level?
No, so we didn't do any calculation. We're just arguing that if you are at the band, outside the band edge, this many-body interaction, even if you add and calculate transport scaling outside the band edge, you should not see any change of scaling. But that's not true if you are calculating what is the effect of this within the band, because within the band you have number of particles which is scaling with the system size. It's an extensive number of particles. Yeah, so then this many-body interaction will contribute tremendously. And
I thought that you have the interaction within the system.
Sorry?
I thought that you have the interaction within the system.
Yeah. So this is the interaction within the system. But I'm arguing that if you put this interaction and calculate scaling of conductance outside the band edge, because the system doesn't have extensive number of particles, and if you make large n, effectively this interaction will not going to play much role. So,
yeah. So in the case where you have just short range hopping and your chemical potential is outside the band edge, then you have something that's exponentially. So the length scale in that exponential is just set by the detuning of the chemical potential from the band edge. Is it what sets the length scale there?
That's a good point. I think it's the gap. Yeah, so I can give you another answer. I mean, if you look at this from transfer matrix picture, is basically if you take the tight binding lattice, I mean, you can you can write down the transfer matrix, and these transfer matrix eigenvalues are what essentially, whether they are oscillatory versus whether they are exponential, is what going to give you these scalings. Right. So the localization length essentially depends on this eigenvalue, and I think I'm forgetting, but yes, it depends on the distance.
It'll have to, of course, depend on how far below the band.
Yeah. So
what else, and like
exactly
that into a length scale.
Yeah.
Questions?
So, Bijay, this regarding this question of Srijit and Sthitadhi, this density of states. So you have this Van Hoff singularities. You'll probably get Van Hoff singularities, and the nature of the singularity might depend on alpha. Yeah. I'm talking about the first part of your talk.
Yeah.
So that how it diverges will probably depend on alpha. But then that 1 over n square is universal.
Yeah.
So is the statement that there is no relation between the nature of singularity and transport, or?
Interesting question, but I do not know the answer.
Because for infinite alpha, you'll get a square root singularity.
Yeah, and so it looks like somehow how it diverges near the edges has no information, or at least when you're looking at the conductance scaling. Yeah, I mean, but yeah, I do not have any sort of an intuition or. Yeah, somehow it's super universal if you sit at the band edge. So band edge is actually the energy of the lattice. The energy corresponds to the infinite when you take the infinite limit, thermodynamic limit of the system. So if you have tight binding, so it's basically, and if J is the hopping, so it's minus 2J or plus 2J. So you have to sit there. K equal to 0 mode. So you're talking short range or long range? Ah. See, there is a catch. The catch is that my system is finite. It's n, which would be large, but that n is not going to infinity. But you see, I can tune my mu. So I'm saying when that mu, so because I have the finite reservoirs, so I can tune these chemical potentials. So when this mu corresponds to the thermodynamic limit band edge energy, thermodynamic limit of the system. So the energy is given by these zeta functions, right?
It will be zeta functions.
Is a zeta function, right? So if you take alpha greater than 1, if you take alpha greater than 1, this is not diverging. Yeah, so I'm always alpha greater than 1. So I never took, because alpha less than 1 is a completely different game because you have to, the energy is super extensive, you have to do this Kark rescaling and all that. So that's why, I mean, it's always alpha greater than 1. So. Oh no, I had it in the paper, we had it, but yeah, sorry, I forgot to put it. No, so it has like a cusp kind of a, so if I remember correctly, it has like a yeah, 0 and pi. No, but not within the band, right? Wherever it was L, it still remains L. So within the band, it is still ballistic. Okay. The property got changed just outside the band, if you think, which was exponentially localized, becomes subdiffusive. So, and one intuition that one could have is like, you are setting your chemical potential outside the band, because your system is now dressed due to the bath, and if a particle hops due to some quantum fluctuation or whatever, then what this n by 2 alpha is essentially saying that the particle just makes one long range hop of amplitude 1 by n alpha, which is sitting in the Hamiltonian, and escapes to the other end. So
if you have a classical model like this, do you know what happens to transport if you inject particle and there is long range hopping?
that's a good question, but how do I look at the mu, for example, in that case? Yeah, so that's, see, for example, if you take this 0 temperature situation and if you try to ask whether Lindblad captures this physics, Lindblad setup, the answer is no. So you have to be, yeah, this is a very sort of a unique sort of a setup where you get to see this physics. You will not get these phases. No, so basically that's very simple because if you add, let's say, local Lindblad, so you gonna add these rates, right? So C dragger with gamma, so let's say, so you're gonna have D of, let's say, C1 dragger and D of C1, and sorry. Okay, so let's say, yeah, so let's say, yeah, so CL, but this will have rates, right? So this one you're gonna put it probably with rate. Huh? Oh yeah, yeah. So okay. So let's say you put same rates. Now the point is that if you do this, you wanna just capture ballistic transport. Yeah, because what happens is that this is kind of mimicking infinite temperature. So it will get, so the property will get killed because the current will have an integration over the band. And this integration meaning, so you're basically gonna get all the contribution between in the system band. You will get the contributions from the system eigenfrequencies, which will give you, so it will be N0 or L0. So.
Yeah, I guess there are no more questions. Let's thank both the speakers.
Thanks.